Amlankan sir, good morning sir. No problem. Amlankan sir, good morning. Sir, good morning. Mike sir, Mike. Good morning sir, how are you?
I'm fine. How are you?
Rashekar, fine sir.
Happy Diwali.
Happy Diwali sir.
So
कैसा
everything,
चल रहा है सर दिवाली? दिवाली तो कम मना रहा है ना आजकल?
nowadays it's not so great.
Thank
I'll
you sir.
just check whether my presentation is.
You may please.
Okay.
Sir, we will wait for like 9:30 is a schedule. We'll wait for a few minutes. Meanwhile, you can just keep your cover page, sir.
Okay, now I'm just checking that whether it is visible or not.
Yeah, it's visible, sir.
Okay. So are you? Oh, sorry.
Yeah, it's visible, sir. Good.
Now you can see. No
Yeah, sir. Yes, sir.
Okay.
So we'll wait for a few more minutes, sir. Let the participants join.
Yeah, no problem.
9:30 is a scheduled one, right, sir? I'll let
Yeah,
you know like at what time we would start. Like maybe
okay.
hardly 5 minutes. It will take 5 to 10 minutes, sir.
Okay, no problem.
How you're doing, sir? Then?
No, now everything is standstill. There is no movement.
Yeah. The same thing here also.
Yeah.
But people thought of starting this education institution, students and all, but there were some problems occurred in different
Now
states.
the
Like,
students are coming back, so hopefully they will do.
We had a plan of inviting students on campus. It didn't successful because students at the beginning they are given shown willingness, and later they said like, sir, I thought like one of my friend would come, then I would join like this, but no one has come. But still we have taken measures and respective arrangements we made for students arrival on campus. Didn't succeed. So they are on with the same decision, like we would attend after most probably after this December, like that they were telling.
Okay. Now here the PhD students are start coming.
Yeah.
So hopefully other students also will come.
Yeah. PhD, of course. PhD in the sense like we got a limited strength. It's okay, but and of course we can say they are matured guys. Like if you talk about PG students and PhD, they are little matured. But whereas this our BTech students, even though if you put some restrictions, also there may be a lot of scope for them to just mingle and chances of spreading and all.
Okay. It's good for everyone.
Ashok sir is on leave, sir.
Okay.
So let's wait for 5 minutes, sir. I'll come back, sir. Right. Thank you. Amlan sir, we will start slowly, sir.
Yeah, no problem. You can
Yeah,
take. No.
I'll start slowly. Let the people join, sir. Okay. So very good morning, one and all. This is Rajshekhar from Geetam University, Bangalore campus, from the Department of Mechanical Engineering. So I welcome you all and have a warm welcome to this 5-day faculty development program on AICT sponsored Atal Academy faculty development program titled Green Technology and Sustainability Engineering. So my warm welcome to a special welcome to our today's speaker, Dr. Amlan Khar, for sparing his valuable time. And let me introduce Dr. Amlan Khar to this group of faculty development program with consisting of various faculty members as well as students and research scholars also. I feel this as a proud privilege to introduce Dr. Amlan Khar. He's presently working as an assistant professor for IIT Dhanbad. He's from the place Dhanbad, Jharkhand. Dr. Amlan is going to present a work on fabrication of nano-composites with high temperature grain stability in today's session. And let me give you a brief details about Professor Amlan. Professor Amlan has completed his PhD in mechanical engineering from Indian Institute of Science, Bangalore in 2017. So his work on a PhD was micromechanisms associated with friction stir welding of aluminum with titanium. Dr. Amlan has completed his MTech in the year 2011 in the metal forming, metallurgical, and materials engineering from Indian Institute of Technology, Madras, And his title was at the time Lateral Bulging Measurement and Compensation of Laser Cut Press Brake Bend Aluminum, mild steel, and stainless steel sheet materials. And he has completed his BTech in the year 2009 from the Department of Mechanical Engineering, Jalpaiguri Government Engineering College. So professor has done his BTech thesis titled Efficiency Determination of Industrial FBC Boiler and Overall Study of Steam Power Plant on 2008. If I speak about the research experience and various activities under the research Professor Amlankar is dealing, there are many more to mention. To mention a few, Dr. Amlan has done research activities at Osaka University, especially from the institute like Joining and Welding Research Institute, Osaka University, Japan. So he has dealt with a project titled Dissimilar Friction Stir Welding of Aluminum to Steel, in situ visualization of material flow, investigation on fragmentation of steel, and study on kinematic and growth of intermetallic compounds. And he has also involved in some Indo-Russian DST RMES project on development of friction stir welding techniques for joining dissimilar light alloys. And he also been a part of a project sponsored by Boeing India on incremental forming of titanium. So that was titled as Effect of Strain Path on Texture and Mechanical Property Anisotropy. And Professor Amlankan has involved in so many reputed institutions belonging to India, as well as different reputed institutions across the world, taken a part in various research activities across the world related to different reputed research institutions. And Dr. Amlankar has delivered lectures at various national and international conferences, as well as at workshops also. He published more than 100 research articles and in various reputed international journals, having good citation and having good impact factors. So today we are very great to have a professor like Dr. Amlan for today's session. Hope this session on fabrication of nano-composites with high temperature grain stability would help a lot to the participant researchers and faculty members. They are looking forward to kickstart their research. Definitely it would help a lot. So let us invite Dr. Amlankar to this program. So Professor Amlan, so here is once again a warm welcome from Geetham University and the Department of Mechanical Engineering, and also from this AIT Atal Academy. So we welcome you, sir, to this 5-day faculty development program. And I would like to just request Dr. Amlan to start the session. Thank you, sir. Thank you very much.
Thank you, Dr. Shekhar, for your very nice introductions. And I like to say happy Diwali to everyone. And this is the time where on the time which we enjoy. Okay, but at the same time, we need to develop ourselves for the future.
Thank you, sir.
So let's start this session. So today I'll be discussing about some of the fabrication technique of development of the nano-composite. And as well as I will be discussing about the high temperature grain stability of this composite. So this is most of the work has been done while I was doing my PhD at Indian Institute of Science, Bangalore. So I'd like to acknowledge my supervisor, Professor Satish Pikalas and Professor Sattam Sumas for this regard. And as well as I have gained some knowledge from Professor Rustam Kaivasab and Professor Hidesudi Fuji from Russia and Japan. So whatever idea I have gathered from their influence. They have a discussion with them. I have gained a lot of understanding of the subject. And as well as I have been working with some of my colleague and faculty colleague, as well as during my PhD, I have some colleagues. So we are working together. So whatever informations I will be delivering today, it is not about my work, it is the work of whole team. Okay. So so layout of my presentations is, I will start with introductions about nano-composite, and then we'll be discussing about some of the case studies. First one is the polymer derived nano-composite, which is copper-based nano-composite. And the second is the aluminum titanium nanocomposite, which has been developed, which has been developed from welding of aluminum titanium, and in the weld nugget, whatever the composite been developed locally. So what are the different influence of it, and that we'll study. And finally, we'll study the thermal stability of this composite. Okay. So as far as introduction is concerned, you can see we have seen the nanocomposite in different part of the world and day-to-day life, but we don't realize all the time. Okay, so the nanocomposite is a multi-phase solid material where one of the phase has 1, 2, or 3 dimensions of less than 100 nanometer, or substructure having nanoscale represent distance between the different phases that make up the material. Basically, the any phases, the nanocomposite is a part of the composite where one of the constituent is in nanoscale. So nanoscale means we generally defined it is less than 100 nanometers, so that's why it is called nanocomposite. And in different what I can say, in different systems, we have seen nanocomposite in our day-to-day life. Nanocomposite are found in nature as well. For example, in the structure of the abalone cell, and in our bone also we have seen the nanocomposite. The use of nanocomposite, it is material long predates the understanding of the physical and chemical nature of the material. Okay, and we have lot of people have investigated, like for example, one of the researcher, Jose Iacanum, investigated the origin of the depth of the color and the resistance of acid and biocorrosions of Maya blue plant, which is shown here. Let me you can see here, this is the Mayabi paint. Okay, people have investigated how the color has been developed, and it is a corrosion resistance. So it's attributing it to a nanoscale mechanisms by which it is been painted. So what are the important property? The important property in terms of mechanical terms, nanocomposite differ from conventional composite material due to the exceptionally high aspect ratio we obtain. Okay, aspect ratio means surface to volume ratio. And the reinforcing material can be made up of particle, sheet, fiber, polymer, material, and different kind of things. Different kind of material have been mixed together to form a nanocomposite. And in this nanocomposite, the main important factor is the interface between the matrix and the reinforcing particles, or reinforcing whatever the phases you are reinforced. So this interface is very, very important, because during the tensile testing, if the interface is actually subjected to higher amount of residual stress. So to overcome the residual stress, or to sustain the residual stress, the interface properties should be very, very high compared to your matrix material. Otherwise, the interface fracture may take place. So there are different types of composite we have seen. The different types of composite we have seen, but basically to improve, the objective is to improve the strength of the material. Okay, so to improve the strength of the material, the matrix can be reinforced with second phase material to obtain the composite. And we have also discussed that the second phase composite in general is nanoscale in range in case of nanocomposite. And there are different types of nanocomposite has been found, or has been worked on. This is ceramic composite, ceramic matrix composite, metal matrix composite, polymer matrix composite, magnetic nano-composite, and heat resistance nano-composite. These are few, but first, the first three, that ceramic matrix composite, metal matrix composite, and polymer matrix composite, these are the three matrix composite which has been extensively used or extensively worked on. So, for example, metal matrix composite. If you take the metal have used as a structural component in metal matrix composite for several reasons, because of high modulus of elasticity, dimensional stability, and high specific strength, formability, and machinability. And but there are, it has been found that there are many composite, many structural component has been found where the metal are prone to corrosions, wear and thermal softening also have been observed at elevated temperature. So to improve their property of the metal, the composite has been developed. So how it been developed in case of metal matrix composite? By adding second phase material. It's not a polymer or not a ceramic, it is a material. So what we obtained property like strength, wear, creep resistance can be further improved in that composite material. The commonly used matrix material is the objective is to achieve the high specific strength, and that's why the low density materials such as aluminum, magnesium, titanium are mostly used. The reinforcing material can be metallic, intermetallic, or ceramic. They can be in the form of particulate, whisker, fiber, or laminates. In case of ceramic matrix composite, the ceramics are inorganic, carbide and nitride, which is very, very hard compared to the metal, and they are stiff and high temperature resistance. And they have but the problem is, since they are brittle in nature, they have very low fracture toughness. Hence, to improve the fracture toughness of this material, the particles, whisker, and fibers are added to the composite or the ceramics to have the ceramic matrix composite. In case of polymer matrix composite, a polymer is a matrix. So the polymer is a large molecule made up of chain or rings which are linked together as a substructure, which are called nanomers. So polymer usually have low melting and boiling point because the molecules consist of many monomer. Polymer tend to have high molecular mass. The mechanical and thermal behavior of the polymer largely depends on the cross-linking area, depend on how the cross-link been taking place. Okay, so therefore polymer generally have very high fracture toughness or the toughness because it would elongate as much as possible. So due to the elongation, the fracture or the toughness of the material depend on the stress strain behavior of the material. In a material, if the stress and strain, the multiplication of the stress and the plastic strain define the toughness. In general, polymer have low strength and stiffness irrespective of the entanglement or the cross-linking. And to improve the stiffness of the polymer, they are reinforced with particulate fillets or whisker, glass, carbon fiber, or what is called nanofibers like carbon nanotubes. Okay, so therefore, regardless of the reinforcing these polymers, the strength, stiffness are not comparable to the metal, and the temperature range within which they are physically and chemically stable is quite small. So therefore, we use some sort of filler material to improve the property of the polymer matrix composite. And in addition to that, in case of metal matrix composite, we generally the fillers could be whisker, fiber, and particulates also, or could be intermetallic phases. Intermetallic is also considered as a metal. Okay, and because of this reinforcement, metal matrix composite is metal matrix composite property substantially improved. Okay, so there are different manufacturing methods or the synthesis method to have a metal matrix composite, and we can see here there is a molten state methods, and there is solid state method. The molten state method is the casting, liquid infiltrations, spray deposition, in situ processing. You know the spray depositions means you mold the metal. After that, the particulates as well as the molten metal is being sprayed on a substrate to get a composite material. It is a deposition method. Okay, and similarly, there are different solid state methods are also available, like powder metallurgy, diffusion bonding. This is the two solid state method process, and the deformation method also used, like extrusions, accumulative roll bonding, and combination of both you can get friction stir welding method or friction stir processing method. Okay, so these are the different methods through which you can get a metal matrix composite. So first of all, we are discussing about the polymer derived nano-composite of the copper based. We have work on also on aluminum with the same methodology. So what are the method? This is the friction stir welding method. This is the solid state welding method through which the nano-composite has been fabricated. So what are the different steps in the why the friction stir welding method is very useful? Because solid state method have gained a lot of interest at the recent past, because the issue related to the melting of the material and the solidification, like solidification defects or porosity, can be substantially reduced using the solid state method. So one of the popular solid state method is the powder metallurgy method. The powder of both the matrix and the reinforcement are mixed together and compacted, followed by sintering at high temperature. In this process, porosity in the matrix is the common issue, and this is the main problem. Okay, so therefore, the high pressure torsion or high pressure extrusions or high pressure sintering people have been used extensively to overcome this problem. Okay, but since the friction stir welding have the high pressure, use the high pressure method or high pressure technology as well as the shear deformations. So therefore, at recent past, friction stir welding or friction stir processing method have been extensively used in case of welding, in case of development of the composite. So as I was discussing, that friction stir combine the frictional heating and the stirring motion to soften and mix the interface between the two pieces in case of welding. And if you are incorporating the second phase particle, it's a mixing of the matrix material as well along with the particles. So therefore, we generally get a composite material locally. The principle is very simple. The first, you can see here in the figure A, the part are mated together. You can see it is mated together and clamped rapidly. At the interface, you give some particles. Okay, and then you can see a rigidly cylindrical spinning tool composed of protruding pin, and the solder is actually plunged into the line at which you want to deform the material as well as the particle. Okay, and this is the plunging phase, and after that there is a dwelling phase. After the plunging is complete, you can see the plunging being occurs, and after the plunging the dwelling phase started, and in this dwelling phase the material gets softened due to the frictional heating between the tool, and since it is rotating, there is a relative motion between the tool and the material that lead to the soften the base material or the matrix material, and then tool is traversed across the interface. Okay, and it's physically deformed steel around the tool. Whatever the particles are there as well as the matrix material is physically deformed, and it is steered around the tool pin, and further it is consolidated because there is whatever the deforming material, it is been confined by the tool solder. Okay, so if I show you one of the process, then you can understand. I think you cannot see. Okay, sorry. Let me show you the process. Yeah. So video is not coming. 1 minute. I think there is a issue, some issue, that's why PT is not able to show. Okay. So basically this is the process, and after the processing you can see there is different kind of phases being formed, and in sense you can see there each grain refinement because of high deformation energy been putting, and there is a high strain deformation, high strain and strain rate deformation. Because of that there is you can say that in the matrix material you are getting the reinforcement particle as well as there is a grain refinement. Okay, so if a material is subjected to grain refinement, then due to the Hall-Page equation, you know, means Hall-Page equations define that if the grain size of the material decreases, there is an improvement in the mechanical strength. So since in the oil nugget or the zone or the processing zone, you can see that the microstructure is very, very fine, you can expect a better mechanical property. As well as you can see you are adding some reinforcing particle like ceramic particles or the metal particles. So because of this particle also there is an improvement in the mechanical property, and which we can see by conventional method also, like powder metallurgy load. So if you add some particles homogeneously, then there is an improvement in the mechanical property. So there is a two-way advantage you are getting in this particular case. So ultimately you are getting the composite property in the nugget zone. If you consider this is the welding, okay, so the center of the zone is subjected to some sort of welding. So this is the particularly very useful method for repairing work, and as well as if you want to improve the mechanical property of certain locations of your component, then this is the very ideal method to improve the property of the particular locations. Because if you go to some other means, some other welding means or during the repairing work, then what will happen, due to the heat affected zones and due to the melting of the material, there is associated defect arise. like solidification defects, porosity, residual stress. These all sort of problems will come into picture. But since the mechanical or the temperature evolution in this particular case is much lower than the mechanical, much lower than the melting point of the material, then the problem due to the solidifications does not come into picture. And since the temperature is very low, so then you can overcome the residual stress substantially. So therefore, this is the process where you can develop the local composite in a particular location where you need improvement in the mechanical property. So how you develop the polymer derived ceramic? Generally you get a nano precursor. This is the nano precursor you can get from the market, and after that you it is subjected to cross linking. Okay, it is also called pyrolyzations. Okay, let me discuss. So PDC processing include means here I have included the 3 steps, the basic step. The first is the synthesization or the modify the polymer precursor. The second step is the shape and cross-link to form infusible polymer component, and the third step is to convert the polymer component to ceramic by heat treatment at a particular temperature. Okay, so in the present case we have heat treated at 1000 degrees centigrade. So material obtained in this case is primarily amorphous material, and since you know during the pyrolyzation it is subjected to high temperature, there is a possibility of formation of different, what I can say, different voids or pores in the polymers. Okay, there are 2 known polymer derived ceramics are available. One is silicon oxide carbon system and other are silicon nitrogen based system. The other elements are boron, aluminium can also be incorporated into the network for modifying or improvement in the mechanical property. The polymer derived ceramics have many advantages over the traditional powder based ceramic process, because the fracture toughness of these ceramics are very low because of formation of different type of pores. Okay, so after the synthesis you are getting some sort of silicon SiCN ceramic particles from the polymer root, and it can be expressed in this form. You can see here where N is the specific ratio of the stoichiometric. So that depends on how you are preparing the ceramic particles. So if you see the mechanical property, you can find out the mechanical property of the silicon carbide SiCN is more or less comparable to the other ceramic particles, but you can see the fracture toughness or the toughness of the material is substantially low compared to the SiC, Si3N4. These are the mostly commonly used ceramic particles. And one of the important factor, you can see the thermal property is very high and porosity is very low. These are the factors which has been considered during the fabrication of the composite. And mechanical properties like hardness and modulus of elasticity, you can see it is much comparable to the other particles. So you can see the modulus of elasticity is very low compared to the other polymer particles, but it is little higher compared to the silicon oxide particles. So depending on the property, you get a different kind of composite material. So in the present case, we are looking for Si3N4, Si3Cn. The major challenges is that because of the higher hardness of this of the ceramic particles, you know, the hardness I have discussed here, the hardness is very high compared. You can see it is gigapascal. So since the hardness is very high, the material is subjected to some sort of it actually create a wear on the surface of the tool. Okay, so our tool is rotating continuously. So when this tool material is come in contact with ceramic particles, so ceramic particle create a crater on the surface, and therefore the surface of the tool is subjected to wear and tear. So here you can see some of the, this is the main challenge in case of ceramic matrix composite. So therefore, if you directly incorporate the particle, ceramic particle in the matrix, and then you do the processing, this is very difficult to obtain a homogeneous property from the beginning to the end of the process, because you can see depending on the length of the process, the features of the tool changes. Because of the change in the tool features, there is a change in the mixing of the particles in the matrix, and therefore there is a possibility having difference in the physical property of the material. So then the objective is to how you can overcome this problem. This problem can be overcome, we can see in this process. So here the polymer particle, what we are getting, the polymer particle is directly incorporated or into the matrix material. You can see this is the matrix material, copper, and the polymer. You are cutting a groove, and on the groove the polymer particle has been filled. After filling the polymer particle, you do the process, the friction state process, whatever we used to do, that have been conducted. Since the polymer particle have very low fracture toughness, it does not wear out the tool material very easily. Okay, so ceramic particle hardness is very high, but the hardness of the polymer particle, which has been obtained in this process, is not substantial. So therefore, you can overcome that wear of the tooling, and therefore we can obtain a homogeneous property of the composite which has been fabricated. So there is a different step is there. The first step is this one, and therefore you processed it, and after processing you pyrolyzed. After processing, during the friction state processing, you can assuming that this polymer particle, which is having the low fracture toughness, is subjected to fractures, and during the fractures, while fracturing the particles, this is converted to very nano sized particles. We'll come into that, since this polymer particle having low fracture toughness, and it could easily distributed or easily consolidated in the process zone, the nanoparticles, and after that you pyrolyzed the ceramic polymer particle, so that the polymer particle is converted to ceramic. Since it is a nanograin size of the polymer particle, when this is subjected to pyrolysis, that nano-sized polymer is converted to nano-sized ceramic particles. And then if you process it, then there is no possibility of wear of the tool, and hence we get a complete nano-composite. So what I am telling, after pyrolysis, the sample are processed again using the same process parameter to distribute the ceramic powder and remove the porosity if it is available, but generally the porosity is available in the particle because when it is subjected to pyrolysis, so whatever the gas been evolved from the polymer, that actually create or develop porosity inside the matrix. So to overcome this porosity effect, so again the third pass or the additional friction state processing or friction state processing has been conducted to eliminate the porosity. So this is the sample dimension. You can see from the interface, from the center we have taken the sample. This is the dimension. So this dimension is specifically chosen to measure the mechanical property of the center portions. Okay. And this is the composite being developed, my colleague. And you can see this is the center portions. From there you can take out the sample and get the microstructure. So this is the as received copper and processed copper without the polymer particle or the ceramic particle. You can see here that after the processing, this is the base metal, the microstructure, the grain size was approximately 20 microns. After the processing of the first pass, second pass, third pass, and fourth pass, you can see after the second pass, you get a very good refinement of the grain structure. But if you go for further processing, because of the higher heat input, there is a grain refinement being taken place. You can see. After the deformations, you can see there is a substantial amount of grain refinement. But if you add additional process or additional friction state processing, then there is an improvement, there is an increase in the grain size due to the higher heat input. So therefore, the important to have a process optimizations. You can see the microhardness. Since the increase after the fourth pass, there is an increase in the grain size. You can see there is a reduction in the microhardness. And you can see the polymer particles after the processing. First pass, second pass, you can see there is some sort of pores. You can see in the figure, you can see the uniformly dispersion of the polymer particles. Nanoparticles is a nanometer in range, fewer in the micrometer in range, but many we have seen this is a small particle. You can see these are nanometer in range. And this is the after third pass, and this is the after fourth pass. You can see if you take the polymer particle and you process it, you can the nano-composite can be obtained after the fourth pass, and we can overcome it the defect formations also, defect in the sense of porosity. And if you see the particles, number of particles after first pass and the intermediate pass and the fourth pass, you can see after the fourth pass there is an increase in the number of very fine particles, and this is because of continuous fragmentation of the polymer particle, which is having, as I discussed, which is having low fracture toughness. Because of the low fracture toughness, it gets fragmented, and because of the fragmentation, the coarse particle which has been there, that is subjected to nano-sized particles. nano size polymer particle that is been consolidated and distributed in the metal matrix. And you can see when this polymer particles is there is an improvement in the microhardness a little bit, not substantially. Okay. So to understand that pyrolysis temperatures, our colleague has done some sort of TAG analysis. Okay, from there we can understood that the pyrolysis temperature or the degradations start at 673 and it's end around 1023 Kelvin. Within this temperature there is a degradations. Okay, and that means this is the temperature at which there is a mass loss of the composite being taken place, and this mass loss is nothing but due to pyrolysis of the composite material or pyrolysis of the polymer material. So then we have also calculated the temperature of the process, and we have seen the temperature is around 923 or 923 degrees centigrade, and this is within the range of pyrolysis temperature. So we can understand that during the process itself, some of the particle might be converted to the ceramic, and these particles are nothing but is very nano grain size particle or nano size particle which has been developed during the process. Why I'm telling why only the nano grain size particle are subjected to pyrolysis very easily? That is nothing but the nano grain size particle have higher aspect ratio, so the activity range is also improved substantially because of the higher activations of this nano grain size particle. This is subjected to pyrolysis very easily, the activation energy for the pyrolysis is substantially reduced, and therefore it is subjected to pyrolysis and lead to the ceramic very easily. And we have seen from the phase analysis that there is a formation of different sort of compound SiCN, because SiCN also have been seen. Cu we obtain, Cu SiCN also been obtained. So you can see different pores been formed in the intermediate stage. Okay, and we can see also the pores been formed inside the particle as well. Okay, you can see the pores. And during the deformation process, since the friction state is a high standard deformation process, during the deformation process, this whatever the crack been developed inside the particle, it is actually propagated further. And because of the propagation of the crack, this individual layer is subjected to fragmentations. And because of the fragmentation, you can see that smaller grain size, smaller particles are also found in the composite material. Okay. So basically, because of this fine distributions of the particle and because of the pores, this cracking of the particle take place during the deformation, and therefore we obtain a fine particle distributions in the final composite matrix. And after the pyrolysis, you can see there is no change in the hardness. Why there is no change in hardness? Because of the availability of a high fraction of pores in the composite. Because of the high fraction of pores in the composite, during the hardness or during the indentations, it does not resist the indentation load because of the pore available in the composite, and therefore there is no increase in the hardness. And this is the microstructure. Macrostructure, you can see After the first pass, this is inhomogeneously distributed, but after the fourth pass, you can see their distribution is more or less homogeneous. And you can see also there is a distribution. This is the first pass and this is the final pass. In the final pass, you can see the particles or the reinforcing particle is substantially reduced. And the size is very, very small. Okay. And the distribution is the Gaussian sort of distribution, you can see. And this sort of distribution very, very useful in metal matrix composite, because this sort of distribution give the property, the useful property or the balance property in the metal matrix composite. And this sort of this Gaussian sort of distribution you can find in the top of the sample, middle of the sample, and the bottom of the sample. Because of the homogeneous distribution, we get homogeneous property from the top to the bottom of the sample or bottom of the composite. And this is the microstructure. You can see this is the EPST image. From there, you can easily find out the microstructure is start from something about 100 micron to the 1 micron. Even it's the microstructure of the matrix material I'm talking about. It is very, very fine. The average grain size is around 1 or 1.2 microns. Okay. So the microstructure initially, the microstructure of the base material initially we have taken was how much? It was approximately 74 microns. But after the process, the microstructure of the matrix material itself, it is very, very fine. So according to Hall-Page relation, we can expect a better mechanical property if we don't consider the matrix influence. If we don't consider the reinforcing influence. Depending on the reinforcing particle, the property could have been improved further. And this is, you can see there is a different type of grain boundary you can see. Here the different grain boundary you can see. There are three kinds of grain boundary can be visible. One is subsurface grain boundary, low angle grain boundary, and high angle grain boundary. So depending on the color, you can find out the what kind of grain boundary has been developed during the process. From there, you can easily find out that 80% of the grains are surrounded by high angle grain boundary, which is represented with the help of blue color here. So since any material is having surrounded by high angle grain boundary, that means it is a recrystallized microstructure. And from the Gauss map, the right side we have represented, and you can see here the Gauss map actually represents how much dislocation has been accumulated inside the grain. So from there you can see the 0.0 to 2 range. The minimum is 0 and the maximum is 2. That means the color representing blue and the green actually representing it actually represents the recrystallized grain. So you can see that almost 80% of grains in the matrix material is recrystallized. So since the matrix material is completely recrystallized, we can expect better ductility. This is just a representation of what we have seen. We can see here the Gauss corresponding to with 0 to 1 degree of Gauss value. The grains with 0 to 1 degree of Gauss value is very, very high in case of very fine grains, which have grain size of 0 to 1 microns. Okay, so these grains is actually the completely recrystallized grains. But the coarse grain, which has not been completely recrystallized, we can see the 4 to 5 micron is the maximum grain size, where the Gauss values are very, very high. So that means it is subjected to deformations. So this is the continuous deformation process, and the bigger grains actually subjected to shear deformations, and because of the shear deformations, it's actually get not fragmented. It converted to smaller grain size because of continuous dynamic recrystallizations, and because of the grain rotations as well as evolution of the sub grains or the grain boundary, sub-grain boundary. That's mean the grain boundary corresponding to blue and the blue and green. This is actually accumulating the dislocation density, and because of the accumulation of the dislocation density, the orientation deviation across the grains actually increases. Because of the increase in the orientation deviation, this grain boundary actually converted from low angle grain boundary to the high angle grain boundary. In this process, the single grain actually refined further to the smaller grains, and therefore we get a refined microstructure which has been observed here. So the fracture mechanism, what we have discussed, we can see here as well. You can see this is the particles which has been consolidated in the matrix, and this is the shear layers. Also we can see that the shear deformations been taking place on the particles, and because of the shear deformations there is a fracture been taking place. And this is the fracture particle. You can see how one particle been fragmented during the process, and because of the fracture you can, this is the TM image. From there you can see the particles. There are many particles where the particle size is approximately 40 nanometers. So therefore this is the innovative way of fabricating nano-composite. And from the compositional analysis you can see that this is the homogeneous distribution of the particles. This is the 20 micron, this is almost 100 micron by 150 micron sample. From there you can see easily that even in the big sample, the homogeneous distribution of the second phase particle, which is SiCN, can be clearly visible. So this is a fabrication of homogeneous ceramic matrix composites, which has been derived from the polymer particles. And because after the final pass, after if you find some pores and all, you do a second pass or additional pass, then the pores and any defect present in the interface of the aluminum of the particle and the matrix, as well as in the matrix or in the particle, which been eliminated. So therefore after the final pass you can get a very good microhardness property of the material, which is close to 2.6 gigapascal. This is very, very high. If you compare with respect to the initial base metal, initial process copper, it is almost 3 to 4 times increase in the hardness property. So what are the, and from compared to the copper also there is an improvement in the nano hardness property of the particles. What are the reasons for that? Because we are getting the advantage of matrix refinement as well as particle refinements. The particle which has been in nanometers range, where because it is nanometer range, we already discussed the surface to volume ratio is very, very high, or the aspect ratio of these particles also very, very high. So therefore we can get a activity at the interface level also, and therefore the bond between the particle and the matrix is very, very strong, and therefore we get a very good mechanical property, like mechanical property in terms of yield strength, elongation, and the UTS. Elongation is very, very high because the matrix material itself is completely recrystallized, and because of O1 strengthening as well, because in O1 strengthening the comparatively bigger size particles or the micro range particle size actually restrict the grain boundary mobility or the dislocation mobility. Because of that, there is an increase in generation of dislocation. In addition to that, the dislocation could move further or pass through as well. So because of these two factors, there is an increase in the mechanical property in terms of tensile strength and elongations. And since we know that if any material have higher elongation as well as the tensile property, so the area under the testing diagram also will improve or enhance. So from there we can conclude that the toughness of this composite will be very, very high. So what are the different strengthening mechanisms generally seen in case of metal matrix composite? There are different strengthening mechanisms being active, and these are Oron, as I have been discussing. This is the Oron strengthening mechanisms. Okay. Grain strengthening mechanism, substructure strengthening, queen strengthening, resulting from the dislocation generated to accommodate the difference between the coefficient of thermal expansion between matrix and the particles. And load bearing capacity of the particle is generally very, very high. So during the deformation, if the particles are very, very small, the load bearing capacity of the particle is very, very high. So load is transferred from the matrix to the particle if the interface is very, very strong. And this is also due to the strain misfit between the elastic reinforcing particle and the plastic matrix. So you see the same thing when you try to elongate. So since the matrix is plastic in nature, so it is easy to elongate, but not the particle, which is the particle is ceramic in nature. So it is a brittle particle most of the cases. So since it is a brittle particle, it is not subjected to elongations, and the load is transferred. Therefore, the load is transferred from the particles or from the matrix to the particles. So grain strengthening mechanisms, it is occurs to the grain refinements, and this is the equations. Delta sigma, the increase in the strength is sigma naught plus k lambda to the power minus half. So lambda is nothing but a distance between two particles or distance between two dislocations. And we can associate it, we can convert it the lambda equal to 1 by d. D is actually the diameter of the particles. So from there you can understood that when the diameter of the particle or the grain size of the particles or grain size of the matrix is reduced, then there is an increase in the strengthening. And for the Oron strengthening mechanism, this is the lambda is again the distance between two particles. Oron strengthening mechanism occurs because of the particles, and grain strengthening occur because of the matrix. So Oron strengthening mechanism, the lambda is distance between two particles. Because of the distance between two particles continuously reduced, because of the formation of Oron looping, so there is an increase in the strengthening. So these are the different strengthening mechanisms by which the microstructure or the material strengthen, the nano-composite strengthening. So this is the schematic view. You can see this is the microstructure, and the particles are consolidated at inside and the grain boundary as well. So this is the TM image. From here you can understood that this is the pin dislocation. This is the dislocations. This is the particle. So dislocation being pinned by the particle, and when the dislocation could not pass through, so it's form a dislocation tangle. And this is, you can see one grain boundary, and it has been pinned by the particles. So these are the different natures we have seen in the nano-composite. This is the same thing on the mechanism. We can see in the fractograph also we have seen that there is a different particles. And when the growth of any voids take place, the particle actually hinder the dislocation moment. And that lead to the increase in the mechanical property. So now we are discussing about, so this is one part, and now we are moving to the second part. Here we are discussing about the fabrication of nano-composite using friction stir welding. So this is also local, and this is also the fabrications of the thin strip of nano-composite. So basically, this is the process. So when you are taking the two material like titanium and aluminum, so the titanium and aluminum mix together in the process zone, and it form a complete composite along the length. And this is behave like a composite, and we can understand from there how the behavior takes place. So I have already discussed how the deformation takes place. So around the particles there is a plastic zone, and around the particle there is a steering motion. Because of the steering motions and the frictions between the tool and the matrix material, there is a formations of, what I can say, there is formation of mechanical mixing zone in the oil nugget or the process zone, and we generally observe the wear out of the tool and the shear deformation of the material. That are the two phenomena being taking place. So to restrict the wear out of the tool, we have shifted the tool toward the dual melting point material. In this case, we have shifted the tool to the aluminum side so that it has a limited interaction with the titanium, and therefore we can prevent the wear out of the tool. These are extensively used in aerospace industry because of three-dimensional mixing nature of the matrix and the particles. If you take the aluminum titanium, you understand that there is a substantial difference in their mechanical and the physical property, and because of that, aluminum is decrystallized, but the titanium is subjected to some sort of fragmentations. And during the fragmentation, you can see there is a development of the microcrack and the development of the intermediate layer at the interface. And this is some sort of brittle particles which has been fragmented and distributed in the aluminum matrix, and because of that we get a composite property of the weld. So we have estimated the temperature, which is approximately 410 degrees centigrade. Because of this temperature, we can understood that at this temperature the aluminum behave like a plastic material, but this temperature is very, very low for titanium. So that means aluminum, this temperature is close to the melting point of the aluminum, unlike titanium. And so the aluminum, during the deformation, aluminum is subjected to hot deformations, but the titanium is subjected to cold deformation because of the difference in the physical property. And due to that, the aluminum generally is recrystallized, unlike titanium, which is subjected to fragmentations. So that is the schematic view. You can see that in the nugget zones, there is a particles which has been deposited and fragmented, and therefore we get a strip of nano-composite. So you can see the particles, how they are distributed in the nugget zone. Again, you cannot see, I think. And we have also, modeled the process, and we have seen the temperature evolution in this process is close to 410 degree or 450 degrees centigrade. Okay, and one of the important factor we have seen, the temperature below the tool shoulder does not vary much. So during the process, from the one side to the other, from the retreating side to the advancing side, or the advancing side to the retreating side, or in the three-dimensional nature, we can understood that the temperature variation is not substantial in this process. So whatever the mechanism being taking place on the top of the weld is also should be prevalent in the bottom of the weld as well. And this is the structure being developed in the center location. We can see there is a difference in the structure, difference in particle size, but at a different locations, if you try to analyze the particle size, we can find out irrespective of the locations, the morphology or the distribution is similar. And from this distribution, you can see that as the particle size decreases, there is an increase in the number of particles. From there also you can conclude it that if the particles are very, very small during the process, then we have also obtained nano grain size particle like 50 micron grain size, 50 micron particle size particle. So if you take this trend, we can expect that the nanoparticle which has been developed in this process is very, very fine, and these particles, or the number of particles, number of nanoparticles is substantially higher compared to the coarse particle. So as we have discussed that this sort of distributions is very common in different manufacturing process, and in that sense the mechanical property, you can get a combination of the mechanical property. If you have a micron size particle, very fine particle, nano size particle, you get load sharing property, load sharing mechanism prevails. But if the micron size particle is been distributed in a matrix, then you can expect to have higher strengthening, higher ductility because of Oro1 strengthening mechanism. So when you have a distributions in the particle size, then you can expect very good mechanical property of the composite. And this has been seen even in powder metallurgy process as well. So when you have a distributions of coarse particle and the fine particle, then you can get a higher higher density of the particle in the matrix, as well as you can get a better mechanical property. So at the same time, when the particle are being segregated, it is observed that the fine particle is very is homogeneously distributed in the process zone. Here, from there also you can predict that very fine particle, which is we are predicting is nano size particle. This particle should be homogeneously distributed in the process zone, unlike the coarse particle. So the important information or important factor is that how this particle are forming, because the objective is to get nano size particle, and we can see that the coarse particle is subjected to fragmentation in certain locations. So what is the mechanism by which the particle is subjected to fragmentations? So for that we have characterized the titanium, and we have seen that there is the recrystallization. So recrystallization is a very unusual phenomena observed in titanium at 450 degrees centigrade. Okay. So to understand the phenomena by which we can predict or we can engineer the composite, we have understood the continuous development of the titanium, continuous evolution of the microstructure of the titanium. From the base material, you can see this is the microstructure is random, and we can see the grain size is close to 50 microns. As we have come close to the titanium, close to the interface, we can see there is a substantial increase in the twinning. So this is one or two twins we have seen in the microstructure, and from the Gauss value you can see that the most of the grains are completely recrystallized. And this is the CAM map. The CAM map actually show that there is whether there is any dislocation activity in a particular location, and the Gauss map actually show the dislocation, accumulative dislocation inside a grain. So that is the only difference between the Gauss and the CAM map. From here you can understood that microstructure of the base metal is completely recrystallized, and as the material is subjected to higher level of strain closer to the interface, the twinning developed in titanium. Twinning is the additional mode of deformation in titanium. And in the interface, we can see there is completely crystallized microstructure, and because of that, there is a fragmentation also in the particle. You can see this particle is fragmented from this particle. This is the original particle. From here, the A particles are being fragmented, and it is subjected to further fragmentation, and that lead to the formation of very, very fine particles. So the mechanism we have developed is that adiabatic shear band is the only mechanism through which we can explain this phenomena, that there is a formation of adiabatic shear band, and it is noted that in the adiabatic shear band the temperature is very, very high. It's close to 1000 degrees centigrade, and this temperature evolution takes place only on titanium. It's not a global temperature, it's a local temperature in the titanium. So because of the evolution of high temperature in the titanium, it is subjected to recrystallize. It is called dynamic recrystallization. At the same time, since the adiabatic shear band is inhomogeneous deformation process, and that lead to the formation of, or that lead to the development of cracks in the titanium, and while deforming, the propagation of this crack lead to the formation of fine particles, and that's why we get a different kind of particles. And as I already discussed, this fine particles is having higher surface to volume ratio and higher activity, and because of that there is a reduction, in activation energy for reaction to take place, reaction in terms of chemical reaction to take place. Because of the chemical reaction, there is a formation of intermetallics, and these intermetallics specifically form when you have very fine particles in the matrix, and that is the same thing happens here. So we can see here, this is one of the phenomena. We can see this is the adiabatic shear bands, and within the adiabatic shear band we can find very fine recrystallized titanium developed, and this is the recrystallized particle. Because from here you can understood that within the particle there is no dislocation activity being observed, and from there you can understood that this is the adiabatic shear band driven process by which the particles has formed in situ during the deformations, and that led to the formation of in situ formation of fine titanium particles or fine intermetallic particle in the aluminum matrix. So this is the same thing we have discussed, that we can see there is a formation of adiabatic shear band in the interface through which the different particles are formed. This is tomography image from which we can see the particle, how the fragmentation and crack been developed. Okay, and if you think about the matrix material, we have seen the matrix is randomly oriented grains, and this is the aqueous grain. This is completely recrystallized, and you can say it is surrounded by high angle grain boundary. So from there, from this understanding, we can see there is a 78% grain are dynamically recrystallized. So this is the high fraction of grain which is completely recrystallized in the matrix, and where this is the black particles. This is the particle actually. So these particles are actually distributed in the matrix, and all particle has not been captured. These particles above 0.5 microns has been captured in this process. So there is there are possibility of having the very fine particles which has not been captured in this process. So this is the Gauss map. From there you can see that the coarse particle, the Gauss map represent the how much dislocation or how much strain been accumulated in the grain. From there we can see the very fine particle having low Gauss value. That means it is completely recrystallized, and the coarse particles is not been recrystallized. It is having Gauss value higher than 3. So therefore, from there, from this diagram, you can understand that the microstructural development is continuous in nature, and it is taking place from the coarser particle to the finer particles. Okay, so this is the phenomena, and from there you can understood that in the aluminum CDRX, continuous dynamic recrystallization prevails, and that led to the grain refinement, and therefore we get a mechanical property as well. And you can see you have taken very small sample from the well nugget or from the process zone, and from there we can get a very good property. And we have taken at the well because this is the nugget zone. From there we get a very good mechanical properties. And you can see the particles are still embedded in the matrix. Okay, after the fracture also, from there we can understood that the interface property of the particles are good. Okay, now I'm moving to the grain stability of whatever the composite we have developed. So whatever the composite we have developed, it's subjected to the high temperature at 500 degrees centigrade for 60 minutes. And this is the location of the composite or the nugget zones, and this is the outside zones. So from there you can understood where the particles are actually distributed very nicely. From there the grains are not subjected to grain growth. Okay, because of the particles are actually sitting at the grain boundary, and it's spinning the grain boundary mobility, which is very, very important for grain boundary mobility or the grain growth. So the particle actually hindering the grain boundary mobility, and therefore we obtain a very good grain stability. This schematically I have represented here. We can see the some of the particles is actually sitting at the grain boundary, as well as the particle are sitting at the matrix material. So from there you can understood that the fine particle, which is mostly the intermetallic particle, which is having high temperature grain stability, which does not degrade and which does not degrade as well as react at a high temperature. So this particle actually sitting at the grain boundary and pinning the grain boundary mobility. The same thing has been also observed when the titanium particles are distributed in the matrix material. You can see here, this is the outside the matrix, and this is the process zone. From there you can see that grain stability is substantially higher in the composite material. So what are the mechanisms of the grain stability in the metal matrix composite? So when you are getting the fine particle, because of the higher shear deformations of the interface, what are the property of the fine particle is the higher surface to volume ratio, and because of that there is a higher reactivity of the particle and the matrix material. And since the titanium particle have low solid solubility in aluminum, so it does not react further and it does not form a solid solutions. Instead of that, it converted to intermetallic, such as Al3Ti. These intermetallic have higher hardness, higher grain stability, phase stability at high temperatures. And since it has low number of slip system, it cannot be sheared off easily. So because of that, this fine particle which is sitting at the grain boundary, being the grain boundary stronger than the titanium particles, okay, and hence we obtain a very good thermal stability or the grain stability of the metal matrix composite, which has been developed in the present case. We also developed thermally stable aluminum based PDC composite. Similar things we have developed in case of copper also. But in this case, the polymer we have taken is different from the polymer we have taken in case of copper. So the polymer, the method and mechanism is same. That you have take the polymer, cross-link the polymer, and this polymer, you develop the polymer particles. Then polymer particle is subjected to fragmentation during the deformations, and basically you are dispersing the polymer particle by FSP process, and then you pyrolyze it. During the pyrolysis, the polymer particle actually converted to ceramics. By the way, during the deformation itself, the polymer particle is converted to ceramic because of low fracture toughness of the polymer. And after pyrolysis, this nanopolymer actually converted to nano ceramic, and it is embedded in the matrix material, which is aluminum. Since there is a lot of defect also, a lot of white also formed during the process, so additional pass has been provided in the composite. So therefore, we get a highly dense composite material, aluminum based PDC composite, polymer derived ceramic composite. We can see after the heat treatment at 500 degrees centigrade, there is no change in the grain structure. And this is the graph which shows that there is distribution of the grain size before and after the heat treatment. And from the Hall based relationship we already discussed, so we can expect better grain stability or better mechanical property of this composite. So as I was discussing, one my colleague has already in details, they have studied and find out that this particle actually nanometer in size, and this nanometer particle, from this figure you can see, this is the nanometer in size, the particle, and actually sitting at the grain boundaries. So therefore, it pin the grain boundary mobility and enhance the grain stability of the nanocomposite. So this is the all about what I was trying to discuss about the nanocomposite. I hope you have understood the process, and if you thank you for your kind attention. If you have any particular questions, I'm ready to answer.
Yes, thank you, Dr. Amlan, for such an enlightening and effective session on fabrication of nanocomposites. I request the participants, if they have any queries or doubts, they can please convey to Dr. Amlan. So as such, sir, there are no questions from that topic. So I suppose all are clear with that.
Okay, if you have any further question in future also, you can send me mail.
Yes, so we'll definitely convey your email ID and all the contact details to the participants. And from the Department of Mechanical Engineering, Geetham School of Technology, Bangalore, we are very grateful for your time and effort you have taken to share your knowledge and valuable expertise on this very important field of study. And the participants surely gained a valuable insight into the fabrication of nanocomposites, and it is surely a huge source of inspiration for the upcoming researchers that are planning to do research in this topic. So I'm sure this would be of great help to others, and we hope it was a positive experience to you as well. And again, my sincere thanks on behalf of our department for supporting our faculty development program, and we are sure we can hope to see you join us again for our future programs.
Thank you, Sandeep, for your concluding remark. But at the same time, if you have any doubt or question, you can ask me.
Yeah, sure, sir.
Okay.
So at present, there are no doubts, but I'll surely convey your email ID and contact address for them. So maybe they have, they are trying to get to you personally. So I'll just convey the mail ID and all the contact details for them to the participants.
Thank you for your time as well, and thank you all the participants for listening to me. Thank you all.
Thank you very much, sir. Thank you. And the participants are requested to join us again through the same link for the next session by Dr. Kulkarni. So we'll be starting again on 11:30. So thank you all. Thank you, Dr. Amlan. Thank you all the participants, and we'll meet again. Thank you.